whole new space race has begun. Over the next decade, the United States, Germany, England, Japan, India, China, Russia, and even a few private companies have plans to send rockets to explore the moon. They will map the lunar surface, search for clues to its origins, and find out what's there that humans can use to survive. A Russian mission will send seismic detectors into the soil to monitor moonquakes and study the flow of heat from the moon's core. A Japanese mission will use X-rays to search for rare minerals. An American mission is prospecting for water in the shadowy craters at the moon's poles. But governments aren't the only ones joining this new race to the moon. With more missions on the drawing boards and the chance to actually make money developing space businesses, private ventures are angling to supply launch or human transport services and even begin exploiting space resources like energy, materials, and the freedom from gravity itself. Private robotics teams vying for the $30 million Google Lunar X Prize are designing, building, and planning to launch rovers with video cameras to explore lunar landscapes. It's inspired by the Orteig Prize that sent Charles Lindbergh flying across the Atlantic Ocean more than 80 years ago. That feat helped launch the civil aviation industry. The sponsors of this prize hope it will unleash the entrepreneurial spirit into space. The goal of these missions is to begin to fulfill a grand promise of the space age: to send humans back to the moon and beyond. To permanently live and work in space. NASA has unveiled its grand plan. It's a series of steps designed to build knowledge and expertise while steadily reducing the risks to human life. For now, it's the space shuttle that takes us up there. It's a big freight hauling system, able to lift over 25 tons of people and machines into space with every launch. On more than 24 flights since 1998, the shuttle has carried the International Space Station into orbit, piece by piece, module by module, solar array by solar array, subsystem by subsystem. But the shuttle has never lived up to its promise of low-cost access to space. And now, a new NASA transportation system is slated to take over. If all goes well, Constellation will transport astronauts back to the moon, on to some of the near-Earth asteroids, eventually to Mars, and perhaps beyond. Aboard Space Station, astronauts are already preparing for longer missions. Figuring out how to keep muscles and bones from weakening and thinning out through exercise and nutrition. Just as important, they're working on technologies that ensure clean air and water, shelter from solar radiation, and flexible spacesuits to work and explore in hostile environments like the moon. The surface of the moon first came into focus 4 centuries ago. The Italian physicist and philosopher Galileo Galilei had heard of an instrument built by Dutch opticians that could see faraway things as if nearby. Galileo, in many ways the first modern scientist, saw this new instrument as a tool to help settle a long-standing question. What was the nature of the heavens? And what was the place of the world of men within it? The moon, to some philosophers, was seen as a perfect crystalline sphere of divine substance, free of any earthly imperfections. In 1609, to help support his science, Galileo began building and selling spyglasses to sea captains and merchant traders. But he himself took aim at the moon. He saw that it had a rocky, textured surface like the Earth, marked by myriad craters, mountains, and ocean-like depressions. The moon, he found, was far from perfect. To Galileo the scientist, it was even better, for it was clearly a world unto itself. Flash forward now, to a time just about 4 decades ago. The astronauts of Apollo piloted down to the lunar surface for the first time. The moon, the Apollo missions discovered, is like a time capsule from the early days of the solar system. Rock samples confirmed a dramatic theory. The moon is actually made of material very similar to the surface of the Earth, likely blasted out more than 4 billion years ago in a violent impact with an early planet that was about the size of Mars. Moreover, the evidence showed that all those moon craters were not ancient volcanoes, as many scientists had believed, but rather they were scars from asteroid and comet impacts. Scientists began to wonder whether those impacts had endowed the moon with resources, such as water, that could be tapped to support long-term missions. The 6 Apollo crews that landed on the moon had all touched down near the equator. The rocks there were bone dry. In fact, all the fine dry dust became a persistent problem by getting into equipment and even sneaking into spacesuits. It turns out that the rocks brought back by Apollo were loaded with hidden treasure: iron oxide, calcium oxide, and other compounds containing oxygen. To confirm this finding, astronomers trained the powerful eyes of the Hubble Space Telescope on the lunar landscape. What could a telescope able to see things 10 billion light-years away tell us about an object so close we can practically reach out and touch it? From its position in orbit, Hubble's instruments are able to read the ultraviolet light that's blocked by the atmosphere. Using Hubble's spectrograph, astronomers could look for the fingerprints of specific minerals. Hubble's first lunar targets, the landing sites of 2 Apollo missions. Samples from these sites, brought back by astronauts, contained a glassy material called ilmenite. It's rich in oxygen. Hubble's data shows that ilmenite is strewn over the areas of these landing sites. Hubble moved on to a second target, the Aristarchus crater, 25 miles wide and about 2 miles deep. Created by an impact just 450 million years ago, a short time in cosmic history, it's one of the youngest large features on the moon. That impact exposed the ground below, and with it, the history of a region rocked long ago by impacts, volcanic explosions, and tectonic shifts. This region, too, is rich in ilmenite, and therefore oxygen. But what about the other element in water, hydrogen? In 1998, the Lunar Prospector, an unmanned satellite, began an ambitious mission to map the lunar surface. With an instrument called a gamma-ray spectrometer, it recorded the telltale signature of a variety of elements. The data showed that hydrogen is spread widely across the poles of the moon. If it's from water ice, millions of tons could well be embedded in the soil there. And there's one place in particular where water may be concentrated. The moon is in what's called tidal lock. Only one side of the moon faces the Earth, and yet As it orbits its mother planet, all sides are bathed by the light of the sun, instantly evaporating any water that might get to the surface. Still, there are places that never receive direct sunlight. The floors and sides of deep craters. These shadowy areas, found mostly around the poles, may well contain stores of ice. One of the best places to look is at the South Pole, especially the famed Shackleton crater. It's named for the fabled explorer of our own South Pole, Ernest Shackleton. If there is ice here, it might have been delivered by the asteroid or comet that hollowed out the crater in the first place, or by others which impacted in other places, spraying the vapor that came to rest here. As important as it is, water may not be the only vital resource for future explorers. Back in July 1969, astronaut Neil Armstrong departed slightly from the mission plan. He scooped up some dirt, known as regolith, used it to fill out an empty space in a sample container, and brought it back to Earth. The dirt had been lying there for millions, if not billions of years, soaking up the sun. Scientists found that solar winds had endowed that dirt with a substance rare on Earth called helium-3, and there's a lot of it there on the moon. So now, Chinese, Russian, Indian, and American planners are all considering ways to mine helium-3 as a potential fuel source for interplanetary travel and even large-scale power generation here on Earth. When people do return to the moon, the poles may offer the best chance of finding water. But try landing there. The light is dim, and sharp shadows turn the ground ink black. Engineers at NASA's Jet Propulsion Lab are working on special sensors to read the landscape and safely guide lunar vehicles to their landing sites. One of them is called LiDAR. It's a laser that emits pulses of light, 8 times per second, to produce a 3D picture of the surface below. On the way down, automated navigation systems will be programmed to avoid rocks and the slopes of craters to find the smoothest places to set down. The job of scoping out safe landing spots now falls to NASA's Lunar Reconnaissance Orbiter in the most ambitious lunar mapping project to date. Like a lunar spy satellite, the LRO is scanning the surface of the moon with a multitude of instruments. It uses a laser to survey the topography. When the light bounces off the surface and returns to the orbiter, its timing and intensity reveal the location of steep slopes and rough terrain, or of level landing spots. Another instrument records the temperature. Where there's lots of loose material, temperatures change more slowly from day to night. So a thermal map can show places where the ground is too rocky or too soft for a landing. Finally, the orbiter trains a high-resolution camera on the surface. This allows mission planners to actually pick out any large boulders. In this simulation, the red areas are clearly unsafe, while the green are smooth and free of hazards. Few places on Earth have been scanned so thoroughly, and within the data, planners hope to uncover places that are not only safe, but worth exploring. Some say that past missions have only scratched the surface of the moon. The LRO mission is designed to change that. The orbiter traveled to the moon rather like a stowaway on a larger space vehicle known as the L-Cross. In October 2009, the L-Cross upper stage will separate, beginning a free fall toward the moon. It's a 2-ton projectile aimed right at Shackleton crater. When the upper stage, moving more than twice as fast as a bullet, hits the surface, it's expected to blast over 2 million pounds of debris into space and leave a crater at least 16 feet deep. The lower stage trails above and behind, equipped with a battery of infrared and visible wavelength cameras. Within seconds of impact, the lower stage will relay its data back to the orbiter, now passing overhead. And back on Earth, ordinary humans won't be left out of the action. Provided the sky is clear, astronomers will look on, with many wielding telescopes that Galileo could only have dreamed of using. With any luck, the orbiter and impactor combination will yield a definitive answer on how much ice is on the surface, how deep it lies underground, and what other resources call out to future generations of explorers and entrepreneurs. Until then, we'll have to content ourselves with images being sent back by the orbiter. Like these craters, thought to be strewn with lava that intruded from the lunar interior. Or these more rounded features near the North Pole. Or these incredible close-ups of Apollo landing sites, with shadows cast by the landers of Apollo 11, 14, 17, and others left behind when astronauts returned to Earth. "40 years ago, the Apollo mission showed that we could overcome Earth's gravity and set foot upon the Moon. But not for long. Now we are making plans to go again. Emboldened by evidence that we can find the natural resources to extend our stay and to extend our reach out into Galileo's solar system and beyond into the wider world.